25.3 is transmutation. Okay, so there's two vocab words. One is just transmutation, the other one is induced transmutation. But transmutation is just when one element becomes another. And so they kind of took the word from biology, mutation, and stuck the prefix trans in front of it, which both of those words mean changing, or from one side to the other, it becomes another element. So if a carbon atom becomes a nitrogen atom, that's a transmutation. If a carbon 14 becomes a nitrogen, that's transmutation. Anything where one element becomes another element is a transmutation. If it doesn't happen naturally, aka a person forced it to happen, then we call it induced transmutation. So Ernest Rutherford was technically the first true alchemist. He was the first person to actually transmutate a substance on purpose. Okay? And that was mentioned in the book. So just make sure you understand what those two definitions are. Okay? And then all of the examples that we did in the previous video are examples of transmutations, where we had one element becoming another element. And so this nuclear stuff kind of just folds in on itself. All transmutations have to obey, like last time we did carbon 14 transmutates through beta decay into a nitrogen 14. So that is an example of a transmutation, and this is a natural transmutation, so it is not induced. Okay, some of them are induced, but that's the difference between the two of those. What I want to focus on for section 3 is nuclear rates. So like we discussed last time, chemical equations, you can change their rates. You can speed them up, slow them down, you can kind of manipulate them to do what you want them to do. You cannot do that with nuclear rates. So what has happened is that every single time we've ever plotted nuclear decay, we always have a starting amount, okay, which we call A0, and the curve always does this. It is not a linear decay, it is an exponential decay. And so as we plotted these, every substance would have a different amount of time. Some of them it's seconds, some of them it's days, some of them it's years. For uranium, it's millions of years. But we noticed a pattern that if this is 1/2 of A, for every substance, it will reach half of its amount in a particular time. And then in that exact same amount of time, it will be exactly 1/4 of the amount it started with. And then in that exact same amount of time, it'll be 1/8 the amount it started at. And so we noticed that for all of these substances, that it always requires a constant amount of time to cut it in half again. And so if you remember from back when we did rates and equilibrium, anything that follows a curve like this means that you have a variable in the exponent. So it will require logs to solve some of these problems. Okay? But let me just define these terms for you. Okay? A by itself is the amount remaining. A0 is the amount at time 0, so your starting amount. And N is the same N from the gas laws unit, which is the number of something. And in the gas law unit, it was the number of moles. But N on these is the number of half-lives. Okay? So this amount of time right here, where it takes that amount of time to remove exactly half, is called a half-life. Okay? Now, your book gave you another equation for this, where it's A0 times 1/2 to the little t over big T. But that little t over big T is just a conversion. If you know the length of the half-life and you know how long you waited, you can convert into half-lives so that you can just use this equation. So I don't need you to memorize both. Just memorize this one. And then if you're ever given 2 times, you just have to convert into half-lives before you can do this. Okay? So we're going to do an example of one. So in your book on page 819, we're going to do number 17. Okay, so if gallium-68 has a half-life of 68.3 minutes, how much of a 10.0 milligram, sample is left after 1 half-life? Or after 2 half-lives? Okay, and then 3 half-lives. So, on this one, we don't really need the half-life time. It's kind of a useless piece of information unless it asks how long will it take to go to that number. So this is just trying to get you to understand how the math works. Okay? So after 1 half-life, that means that the amount remaining should equal the starting amount, 10 milligrams, times 1/2 to the first power. After 2 half-lives, it's going to be the starting amount times 1/2 to the second power. After the 3rd half-life, it'll be 1/2 to the 3rd power. If you have memorized from math class how to square the number 2 or cube it or like hit the powers of 2 really quickly, you can figure out this is 5. Okay. This is going to be 2.5, and this is going to be 1.25 milligrams, because this is going to be 1/2, 1/4, 1/8. So this is a super simple one where this number is kind of meaningless, unless we wanted to ask a follow-up question: how long would it take to go to 1.25 milligrams, which would be exactly 3 half-lives. And this piece of information tells you that 1 half-life is 68.3 minutes. And so then you would just do 3 times 68.3. Okay, so let's see, 3 times 8 is 24. It'd be 205 minutes. It would only have 1.25 milligrams left. Okay, so anytime it gives you a starting amount, you've got to figure out how many half-lives it is, and then you can convert half-lives into time. Okay, some other questions in the next part will be a little bit harder, so we'll do one more of those before we move on to the next one. Okay. So number 19 on the same page. So page 819, number 19. It says to use the half-life given on the table on the page before, which we'll look up in a second, how much of a 1 gram sample of polonium 214 will be remaining after 818 micrograms on the page before, it tells you that the half-life for polonium is 163.7 microseconds. So I want you to notice that we have 2 times for this problem. Anytime you have 2 times, you're going to have to do your conversion first before you can use your math equation. Because our equation is A equals A0 times 1/2 to the number of half-lives, we need to use these 2 numbers to calculate our N. So 818 microseconds, 163.7 microseconds is 1 half-life. And so 818 divided by 163.7 is going to be 5.00 half-lives. Okay? So now this number is N, that number is A0. Okay? And 1/2 to the 5th power should be 32 times smaller. So it should be 1 times 25 to the 5th power. So the amount remaining would be 0.0312 grams. Remaining. Okay. If you're ever given 2 times, your conversion is first, math second. If you're ever given 2 amounts, which is where we get into the electrochemical dating section, it's just figuring out how old it is based off of 2 different amounts. And so what happens is, a question that you would see like that would be, let's see, a sample of a fossil contains %30 of the carbon-14 it started with. How old is the fossil? Okay. So again, you'd have to look up the half-life of carbon-14. Luckily for me, I know that at 2 sig figs it's 5,700 years. Okay? With this 30%, you can get 2 amounts. So all we have is 1 time. So we can't do our conversion first, we're going to have to do our conversion last. And so just like we've done all year long, if it ever gives you a percent, assume 100 grams, and that's the easiest math. So if we assume that we started with 100 grams, then we would only have 30 left at 30%. You can pick any numbers you want, just pick them so that this is 30% of that equals 1/2 to the n. To solve for n, we got to bring this over. So 0.30, which again is your 30% written as a decimal, equals 1/2 to the n. And at this point, it's the same math that we were doing to solve for our reaction rates and our equilibrium constants. You now have to do the log of both sides. Which allows us to pull the n in front. And so n is the log of 0.3 divided by the log of 1/2. I don't need you to show this middle step. Once you get to here, the answer is always the log of the decimal divided by the log of 1/2. And if you do that, you get 1.74 half-lives. Okay? But the question doesn't want to know how many half-lives, it wants to know how old is the fossil. And that's where we can now use this to convert. If we have 1.74 half-lives, we know that one half-life is 5,700 years. And so I get 9,900 years old. So whatever that was a fossil of, if it was a plant, that plant died approximately 10,000 years ago. If it was an animal, you couldn't be a dinosaur because it only died about 10,000 years ago. Okay, one of the things your book doesn't mention a whole bunch, but a general rule is you can only use a substance as long as it fits within 10 half-lives. So once we get past 10 half-lives, there's not enough material to make an accurate reading. So a common misconception is that we use carbon-14 to date the dinosaurs. That is not true. We cannot use carbon-14 to date the dinosaurs because we can only go back 10 half-lives. And so 10 half-lives is about 60,000 years. So you can only use carbon-14 to date anything that died within the last 60,000 years. If you want to go back to dinosaurs in the millions of years, we then bump up to potassium-40 because the half-life of that is actually measured in millions of years. So we're able to be within our 10 half-lives to get as accurate a data as we possibly can. Okay? And this is the math that goes with section 3. It's just a matter of, do you have to do the conversion at the beginning? If it gives you 2 times, it's always the conversion at the beginning. If you only have 1 time to work with, or you have 2 amounts, then you have to do the conversion at the end. But it's the same conversion and it's the same math formula. You just have to know, do I convert first, math second? Or do I do math first, convert second? Okay. And then we get into section 4. Okay. So once we get into section 4, it is now fission and fusion. Okay. So fission and fusion are 2 very specific types of radioactive decay. Fission is when an atom splits into smaller atoms. And fusion is when small atoms combine to a bigger atom. So they are literally the exact opposite of each other. Okay? Your book gives you a little diagram that shows you the most stable atoms in the planet. You just need to know iron is the most stable substance in the universe, which is why if you've taken any astronomy classes, as soon as a star tries to fuse iron, it will explode and become a supernova, because iron is the most stable nucleus there is. It will not allow itself to be fused. Okay? So all you've got to be able to do is, again, go back to our nuclear reactions and make sure you can balance them, okay? But these get messy because if an atom rips apart, it's not going to just rip apart into these nice clean nuclei. You're going to spray some neutrons out. So an example of fission, okay, is if we take uranium-235 and we hit it with a neutron, okay? If we hit uranium-235 with a neutron, and this is how we make our nuclear weapons, what happens is this combines to become a uranium-236. And this is important because uranium-236 is a fissionable isotope. Okay? So this substance is unstable and it will undergo fission. And what happens is, the way it rips itself apart, you get 56 protons in one particle, which is a barium. And you also get 36 protons, which is krypton, with a mass of 92. And you'll notice there's a problem with this because we do have 92 protons. We have all the protons accounted for. But that number plus that number is only 233. And we started with 236. So we are missing 3 objects that have no protons but a mass of 1. Those are neutrons. And so what happens is, once you start a fission reaction, it will go through what we call a chain reaction. We only have to give it 1 neutron, and when that first element, that first atom explodes, it sends out 3 neutrons. Those 3 neutrons all run into another uranium-235, which means we now have 3 of these. They explode, and so by the second generation, you now have 9 neutrons. And then you get 9 of them at once, and then now you have 27. The reaction grows exponentially. Okay? And so what happens is, once it starts, you can't stop it. Okay? It is very, very difficult to stop. There are ways we can speed it up and slow it down. Make sure you read that in the book. It does mention how to speed it up or slow it down. But you'll notice this gets conserved to here, and then all of those have to get conserved there. Okay? For fusion, it's the opposite. You're taking 2 things that are small and you're squishing them together. So for instance, if you were to take a typical lithium atom and you accelerated it and were somehow able to get the lithium nucleus to combine with a beryllium nucleus, you could create something with 7 protons and a mass of 16, which would be a nitrogen isotope. Okay? Now if you were to run the proton or the neutron to proton ratio for that, it would be outside of the band of stability, so then this would probably automatically undergo beta decay to become an oxygen. Okay, so this is probably unstable. And so then it would undergo beta decay to create a stable oxygen 16, and that is the mass of an oxygen atom. Okay? So again, you can create unstable nuclei, or if we had sandwiched instead of a beryllium, if we had done a boron, then we would skip this unstable nucleus and we would just create a stable oxygen atom. But none of the rules change. You've got to have the same number of protons and the same number of neutrons left to right. Okay? And then the second half, okay, gets into Einstein's E equals mc squared. And there's a vocab word that goes with that. Okay? It is called the mass defect. Okay? So it's the amount of mass destroyed in a nuclear reaction. Okay? Notice how up here, 7, 9, 16, those are all whole numbers. Okay? What happens during one of these reactions is that if you actually calculate the exact mass of this lithium atom, it might be 7.00010. The boron might be 9.00010. But this oxygen might be 16.00000. And so if you look at these two numbers, these are not equal. Okay? These numbers add up to 16.00020. And so the mass defect would be the mass at the beginning minus the mass at the end. Okay? Grams. Okay? Or AMUs. Okay, we're just going to pretend like it was grams worth of them. So here's what happens. Okay? We've been doing the law of conservation of mass, saying that the mass can never change during a physical or chemical process. And that is absolutely true, because none of the mass is being converted into energy. There is technically no such thing as the law of conservation of mass. There is only the law of conservation of energy. But in a chemical or physical process, there is zero energy being created by destroying mass. And this was Einstein coming up with this equation and figuring it out was amazing back in the 1900s. He figured out that the energy created by a substance is always its mass times the constant speed of light squared. And so what happens here is that if you multiply this mass defect, which must be in kilograms, so it's 2.0 times 10, this is already to the minus 1, 2, 3, 4, so it's going to be 10 to the minus 7 kilograms. If you plug in that number for the mass, and you multiply it by the constant speed of light squared, which was also back in chapter 5, it's 3.0 times 10 to the 8th squared. And that will tell you how much energy is released. And so even though that's a tiny, 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 tiny amount, if you do 2 times 10 to the negative 7 times 3 times 10 to the 8th squared, you will get 1.8 times 10 to the 10th joules, which is 1.8 times 10 to the 7th kilojoules. So this reaction with only 0.00020 grams of mass undergoing a nuclear change will release 18 million kilojoules. And if you remember from back in the thermochemistry chapter, most of our chemical reactions generate maybe 100 joules. Or sorry, 100 kilojoules. And so you can see this number is very, very, very large for a very, very small amount of mass that goes missing, which is why nuclear reactions always generate massive amounts of energy compared to chemical processes. And the rest of the book explains how we use fission in a nuclear reactor, and there is a way to speed them up and a way to slow them down. Make sure you understand those two things. And then the last section explains why we don't use fusion, even though fusion would generate more energy. If we can figure out how to do fusion, it would end all of our energy problems for the rest of time. But there's a big, big, big problem with trying to use fusion. And so the book explains what it is. I want you to read about it. So make sure you've got that last section squared away on how we use fission and how we control it, and then why we don't use fusion even though mathematically it would be better than fission.